Hello, everyone. Thank you for coming. Today, we're very happy to have Lars Aalsma, who is going to tell us about information recovery and backreaction in de Sitter space. Lars, take it away.
All right. Thanks a lot for the invitation to speak here. So it's a great pleasure to visit UBC, albeit virtually. But I see that there's a very nice hybrid setup. So it still feels a bit like I'm there. So that's very nice. Yeah, so what I would like to tell you about today is some work that I did that's related to information and backreaction in the Sitter space. And it's sort of inspired by some of these recent developments about black holes and the black hole information paradox. So the motivation, I think, is sort of quite clear for the reason why we would like to understand quantum gravity or quantum information in the Sitter space. And that's, of course, because accelerated expansion plays a key role in the history and evolution of our universe. So when we think about our current phase that we're currently undergoing in cosmology, it seems to be well described by a space that is expanding with an accelerating rate. And also when we induce from observations what happened in the very early universe, we seem to be describing a period called inflation, where also accelerated expansion plays a key role. So both the past and also our future universe or accelerated expansion plays a key role there. And the thing that these two phases have in common is that both types of expansions, they are very likely to be driven by a positive vacuum energy. So when we think about inflation, sort of a very vanilla model of slower inflation is that you have some scalar potential, and the scalar field is slowly rolling down this potential, and thereby driving a period of accelerated expansion. And then if we look at our current phase, our observations seem to be consistent with the idea that we're currently dominated by a phase of dark energy. So this would correspond to sort of this more stationary solution, at least to very good approximation. And so this positive vacuum energy that dominates can be described at least approximately by the Sitter space. So that is a maximally symmetric vacuum solution to Einstein's equations with a positive cosmological constant. And at least classically, things are well under control and well understood. However, when you try to include quantum gravity effects in the Sitter space, then you're really opening Pandora's box. There's a host of problems that arises. And just to name a few, because of the presence or the absence of non-gravitating regions in the Sitter space, it's very difficult in the Sitter cosmology to have a good definition of observables, at least not perturbatively. Secondly, and it's also a related problem, there's no good definition of an S matrix that you would like to use to describe scattering experiments, for example. When we think about inflationary models, then typical models of inflation, they are UV sensitive. So they seem to depend sort of what happens at high energy scales. So this can be both a problem, because typically we like to use sort of effective field theory. At the same time, I think it's also sort of an opportunity, because you might be able to probe UV effects using inflation. When we think about the static patch of the Sitter space, then we typically associate the gravitational entropy to the Sitter horizon. And it's sort of puzzling how to think about what the microscopic description of that is. So for black holes, for example, we have a better idea how that works. And finally, when we do want to embed the Sitter space into string theory to sort of address some of these UV issues, it seems to be very difficult to find controlled solutions in string theory that describe the Sitter space, or more generally cosmological solutions. And I think there's sort of still an ongoing debate in the literature if there even exists a single well-controlled de Sitter solution in string theory or not, and that leads to various heated debates. So when you're confronted with these type of problems, with Pandora's box, you might feel like Pandora that this is a hopeless endeavor, and you might regret that you've opened this box. But at the same time, I think it's also a very interesting and very important question. And at least in my opinion, it's one of the biggest challenges for modern theoretical physics to really understand how we should describe quantum gravity in cosmological backgrounds. So how should we make progress? Well, we know that in black hole physics, similar questions can be asked. And there it's the case that probes of quantum information theory, for example, entanglement entropy or complexity, they have been very useful to sort of sharpen our understanding of quantum gravity. And a very famous example is the black hole information paradox, where if we sort of combine gravitational physics together with quantum information theory, we seem to arrive at a paradox, and sort of trying to understand how that paradox is resolved really sharpens our understanding of quantum gravity. And then it's of course a natural question to ask if there are similar paradoxes that play a role in cosmology or in de Sitter space. What we'll see in this talk, we'll assess the presence and a possible resolution of a de Sitter version of the information paradox, with the goal of sort of trying to get a better grip of the microscopic description of de Sitter space. So the outline of my talk will be roughly as follows. So first, I will review a bit for you the black hole information paradox. So I expect that many of you are very familiar with this, but I think it's good to sort of get all on the same page. Then I will discuss some semi-classical effects in de Sitter space that will be important later on. And finally, I will perform a thought experiment that probes the de Sitter entropy in de Sitter space, and we'll try to we'll see how various paradoxes can arise and how they're possibly resolved. So sort of to give you an overview of what the black hole information paradox is. So it turns out that if we treat black holes semi-classically, that they are thermodynamic objects. So you can associate temperature to them, you can associate finite entropy, and they also obey thermodynamic laws. So now you can ask the following question. Let's say that I have a piece of quantum information that I throw inside of the black hole, and I let that black hole evaporate because it has a finite temperature. And let's say that I want to reconstruct that information by performing measurements on the Hawking radiation. Then depending on sort of the type of person that you ask these questions to, you might get different answers. So if I would ask this question to somebody that is more gravitationally inclined, then that person might say, well, we know that semi-classical gravity implies that the Hawking radiation is exactly thermal. And therefore, it can carry no information about the stuff that went into it. So it seems to be impossible to reconstruct that quantum information that I threw inside of the black hole. However, if I would ask the same question to somebody that's more inclined to think in terms of quantum information theory, then that person might tell me that black hole evaporation should be a unitary process. Because if I start from a pure state and I evolve it unitarily, then no information should be destroyed. So there should be some way in which I can reconstruct this information by performing measurements on the Hawking radiation. And this, of course, poses a puzzle because these two statements, as I phrase them now, they are in conflict with each other. Because if the radiation is exactly thermal, it can carry no information, and then this is in conflict with unitary quantum mechanical evolution. So then to solve sort of this information paradox, what we need to do is understand sort of what sort of corrections to these two statements do we need to include in order to make these sort of different viewpoints compatible with each other. So in order to do that, we need to be a bit more precise about exactly what we mean about information. So typically this is phrased in terms of entanglement entropy. So when we define the entanglement entropy, we can think, for example, of some space-like region, and I divide that into two parts. Let's say I have some region A and a complement region AC. Then I can define a quantum state of matter on top of this background. And I can define a reduced density matrix by basically tracing out the region, the complement region of A, such that I'm left with a reduced density matrix that describes the state of matter on this subregion A. Then the entanglement entropy is defined as minus trace rho log rho. And so when this would be a pure state, the entanglement entropy would be 0. And if it's not a pure state, then I find a non-zero value for the entanglement entropy. So when I apply this to a black hole, what we're typically interested in is computing the entanglement entropy associated with the Hawking radiation. And then when you do that computation, you find that there's a large degree of entanglement between the black hole and the radiation. So when you do that computation and you compute the phenomenon entropy using this reduced density matrix, you find a conflict with unitarity. So what you find is that typically the phenomenon entropy of the radiation, it increases linearly with time until the black hole is completely evaporated. However, at the same time, the black hole entropy goes down because the area is getting smaller. And then we know from Page's famous result that unitarity implies that the radiation entropy should be bounded by the black hole entropy. So if the radiation follows this orange curve, then there's a conflict with unitarity. And so resolving the information paradox really amounts to understanding what are the corrections that correct the entropy of the radiation in such a way that it's consistent with unitarity and follows the green curve. And this has been a very interesting field of study in the last couple of years, where there's been a tremendous amount of progress. And basically, the progress that has been made is sort of a refined understanding of precisely how to compute the entropy. And this goes back, for example, to a paper by Engel, Hart, and Wall, where they compute the generalized entropy of some region. So let's say that you have some space-like slice, and maybe to be concrete, you can think of this as a region of ADS space, and it has some boundary. And then the entropy computed at the boundary is then, according to this formula by Engel, Hart, and Wall, is given by the following. So here we are allowing for a possible area term of some codimension 2 surface x divided by 4g, plus the phenomenon entropy on some space-like slice sigma out. And then this formula instructs you to extremise over this of the location of this codimension 2 surface, and then if there are multiple possible contributions, to take the one that gives you the minimum entropy. So if we take ADS, for example, to be in a pure state, then what you find is then the entropy should be 0 because it's a pure state. And then when you extremise this formula, you find that this x basically goes all the way to 0, and then you correctly find that that this formula gives you 0 entropy. So sort of the key insight has been that if we now consider a pure state, and we couple this system to some reservoir system that is non-gravitating, the same formula also gives you the entropy of this reservoir or bed region. But now, because we did this in a pure state, we can consider now the complement region of sigma out, which then amounts to the following formula. So here we see the same formula, but then written in terms of the complement region, which is the union of sigma x and sigma r. So then the key insight is that when you compute the entropy of radiation in this reservoir region, you find that it can receive contribution from these sort of disconnected island regions. So this is the famous island formula. So when you now apply this to a black hole, so here I do this slightly schematically. So here we have an evaporating black hole, and by hand I define some cutoff surface, which is this purple line. And I do this in such a way that I impose transparent boundary conditions here. And then what I want to do is I want to compute the entropy of the Hawking radiation using this formula. So what you then find is you should allow for the possibility that this island region is present, and then you can apply this formula. So this was done in these two papers and also many subsequent papers. And what you then find is that at early times, you find that the trivial island gives the dominant contribution to the entropy. So that is the case when this island region shrinks all the way to 0 size. However, at the Page time, you find that there's a non-trivial island that gives the dominant contribution to the entropy, and that roughly follows the area. So then when you take the minimum of these two contributions, that's when you find the Page curve. And this has been, I guess, the key insight is sort of how to resolve the information paradox, at least for particular types of black hole solutions. And later, this formula was also reproduced, basically using Euclidean techniques, using the Euclidean path integral to see how you can reproduce this formula. Okay, so far that was all probably quite familiar, but sort of to really apply this island formula in a sensible way, we typically want to couple some gravitating region to a non-gravitating bath or reservoir region. And in ADS space, when we think, for example, about the ADS eternal black hole, this arises quite naturally. So I can have some gravitating ADS region, then I can basically glue regions of flat space to the asymptotic boundary, and I can safely apply the island formula. However, if you want to think about similar paradoxes in de Sitter space and compute the entropy in de Sitter space, we immediately find that there's a problem because there are no natural non-gravitating regions in de Sitter space. So you might wonder, how should I apply this island formula? Well, one thing that you can do is you can introduce an auxiliary system by saying I have a disjoint universe that is entangled with this gravitating region. So that is one option. Another thing that you can do is you can try to glue the de Sitter region to flat space at the top. So you give de Sitter space a head. Or what you can do is you can try to modify the geometry either by introducing some matter or introducing a non-trivial quantum state that leads to regions where gravity becomes very weak. What we will do is mostly focus on this possibility to modify the state of matter in de Sitter space in order to generate additional regions where gravity becomes weak. There's been really a quite big literature by now where people have applied sort of all these different types of ideas and also try to understand if these island formulas give you some interesting insight about what happens in cosmological spacetimes. Maybe I should, before I continue, stop to ask if there are any questions. Okay, if not, then I will continue to the next part. So that is the wrong slide. There we go. So when we think about de Sitter space, then it shares some similarities with black holes in the sense that the thermodynamic, that the cosmological horizon also obeys some thermodynamic properties. So this was derived in an old and famous paper by Guinness and Hawking. And so what you find is when you look, for example, at a static, so when you look at the global Penrose diagram of de Sitter space, what we can do is when we think of a particular time slice, then the geometry is described by a sphere. We can pick two antipodal points at a sphere. When we do that, we describe a North Pole and a South Pole. And this North Pole and the South Pole is surrounded by these blue regions, which are the two static patches. So these are sort of the largest regions here for an observer at a pole that is in causal contact with them. And when you when you consider the semiclassical description of this horizon, and similar to a black hole horizon, you find that it has some thermal properties. So you find that the reduced density matrix in particular, it takes a standard thermal form where beta is the inverse temperature of the de Sitter horizon. And in particular, what you find is that because this reduced density matrix contains a non-zero entanglement entropy, you find that the density matrix is mixed in one particular static patch. So what you then can do is you can purify this state by introducing the global and regular so-called Bunch Davies state, which purifies this reduced density matrix to give you a total pure state, basically by maximally entangling these two different static patch regions. However, in a thermal equilibrium state, all the physics becomes time independent, basically because there's no special time where something interesting happens. So if you want to compute the entropy in such a state, that is probably not so interesting because you would expect that there's no evolving situation. So what we want to do in de Sitter space is we want to break this thermal equilibrium in order to generate some non-trivial dynamics. And that might allow you to, for example, compute a page curve. So in order to do this, what we will do is we introduce a modified quantum state. So not the Bunch Davies state, but a slightly different quantum state that only contains incoming radiation. And this state, I think, was first considered in this paper by me, Maulik Parikh, and Jan-Pieter van der Schaar. So one way of thinking about it is if you think of a static patch region, then typically there's an incoming flux of radiation and there's an outgoing flux of radiation. And these two things are exactly equal, such that the net flux is zero. And the inverse temperature of these two fluxes is given by the inverse de Sitter temperature 2 pi L. So what we now do is we define the state in such a way that we set the outgoing flux to 0. So we basically send beta out to infinity, such that there's only incoming flux. And what this describes is the situation where there is some observer that is located at the pole of the Sitter space, and that observer prevents the radiation that is coming in from also to leave the static patch again. So what this results is in a situation where there's radiation that is being collected. So there's a net buildup of positive energy in the static patch. So one way of describing it, for example, in higher dimensions, you can really do this explicitly by introducing a sink at the origin of the static patch, where this radiation is collected. However, there's also a different way of viewing it that was recently explored in this paper by James King, Verheiden, and Verlinde, where they considered a partial reduction from 3-dimensional pure de Sitter space to 2-dimensional JT gravity. And there they found by doing this partial reduction and letting the interface evolve with time, then this dynamically creates this non-equilibrium state that has the same properties as the state that I just described here. What's important, and I already mentioned to you, is because there is this positive energy that is being collected in the static patch, it is clear that at some point backreaction should become important. Because what happens if you collect energy inside of the static patch, the cosmological horizon will start to decrease. And at some point, there will be so much buildup of energy that it might be a possibility that backreaction becomes very large. And that is something that you need to take into account. So this particular non-equilibrium state that I described to you is most easily defined in 2 dimensions, because in that case, the left movers and the right movers become completely independent and can really sort of dial the separate temperatures to be different. So when we look at the Penrose diagram of 2-dimensional de Sitter space, and then sort of because of the structure in 2 dimensions, this Penrose diagram becomes a rectangle instead of a square. So here these blue regions still indicate static patch region. I can define sort of light cone coordinates that are defined as in a single static patch. And I can also define sort of these global light cone coordinates that are very similar to crucial coordinates for a black hole. And then when you compute the stress tensor in the Bunch Davies state expressed in these sort of static patch coordinates, then you find a standard thermal result. And where C here is the central charge of some conformal matter sector that you considered. So here we consider the matter on top of this background to be some 2-dimensional CFT. However, as I just mentioned to you, so the non-equilibrium state that we're interested in is given by taking beta minus to be just the de Sitter temperature. So there's right moving radiation, but then I set the temperature of the left moving radiation to 0. So there's really only a net flux going in one direction. And when you then express the stress tensor in crucial coordinates in this state, you find the following result. So here, if we look at the minus component, this is 0. So this is the same value it would take in the Bunch Davies state. However, we find now that this particular component, the plus component expressed in crucial coordinates, is non-zero, and in particular, it contains a singularity at the past horizon x plus equal to 0. The reason why this singularity is there is because we define the state in such a way that there's basically forever a non-zero flux entering the static patch. So this amounts basically the divergence total flux if you sort of look at it in the entire spacetime. What is important is that this stress tensor also violates the null energy condition, which as a consequence will make sure that the cosmological horizon is decreasing a bit, so that is similar, for example, to Hawking radiation of a black hole that also violates the null energy condition. And as a consequence, a black hole horizon can become smaller. And because of this singularity arises there, which I indicate here with this red line, it makes sense to not think about this additional part of the Penrose diagram, because it seems very difficult to sort of continue the space-time beyond this region where there's this divergence. So effectively, our Penrose diagram becomes a bit smaller. And it is similar to if you would define an Unruh type of state for a black hole, where also, if you take the eternal black hole and we define an Unruh state, there's a similar singularity that arises at the past horizon. So that seems nice, consistent. Are there any questions about the way how I define this non-dynamical state?
Yeah, maybe just asking again. So in higher dimensions, I'm not sure if you'll come back to that, but it's a little bit. I'm a little confused about how the corresponding thing would be. So in 2 dimensions, it seems natural since we have these left and right moving modes. And what would be the corresponding thing? Yeah,
so indeed, so in high dimensions, it's slightly more tricky. So one thing that you can do is consider the S-wave sector in higher dimensions. And then you would sort of have spherical modes that are incoming, and normally sort of in the standard state, they would sort of pass through the origin and be outgoing again. So if you would define this non-equilibrium state, what you would do is you would introduce this sink at the origin. So there would be an incoming mode, but it would not become outgoing again. And also as a consequence of that, you see that there's sort of a singularity that arises at the place where you do this, because you're taking this S-wave mode and you basically shrink it to 0 size.
Okay.
But indeed, so in 2 dimensions, it's a bit more clear because this split in left and right movers is more. Okay, so what we'll now do in order to compute entropy in this sort of dynamical state is to consider JT gravity, because that allows us to include some dynamics, because in 2 dimensions, 2-dimensional gravity is just topological. So it's very nice to consider this dilaton model of gravity, where all the dynamics will be given by a dilaton field. So the action for JT gravity in the Sitter space, it's very similar to the JT action in ADS. So we have some constant piece that we typically think of as describing some entropy of a higher dimensional background that we reduce over. So in this case, for example, what you can consider is a large black hole in 4 dimensions of the Sitter space, and then do the reduction to 2 dimensions. And this would give you the entropy of the horizon there. Then there is some dynamical piece, and now with a positive cosmological constant, we will consider this conformal matter coupling, and then there are also some boundary and counter terms. Okay, so when you look at the equation of motion for this scalar field, you'll find the following result. And then classically, when we, for a moment, turn off the matter contribution, you find that the stress tensor is 0. And then a particular solution that is of interest is this static solution, where R is sort of the spatial coordinate when you consider static coordinates. And you can consider sort of 2 different types of solutions. So one thing that you can consider is if you put this constant piece of the dilaton to 0. So this is typically interpreted as describing a reduction from pure 3-dimensional de Sitter space to 2-dimension. So then your Penrose diagram is just a square. And then there is a region here at I+ where the dilaton diverges. However, we can also consider the situation where this constant piece is non-zero. And then this geometry is more appropriately described as being a reduction from this black hole in 4-dimensional de Sitter to 2 dimensions. The reason is that now you find regions where the dilaton also goes to -infinity. So these are typically interpreted as regions where there is a singularity, because phi effectively determines the inverse gravitational coupling. So we'll consider both types of solutions. So when you look at the equation of motion and you solve for the dilaton in this non-equilibrium state, what you find is, so now there's because we do this coupling with matter, you find there's a central charge here. Then we find sort of the same piece that looks the same as for the classical solution. Now you also have a modification that depends on this Cusco coordinate x plus. And this is what's really giving you time evolution in the state and tells you that you're now working in this non-equilibrium state. What is very interesting is because if you look at this dilaton, you find that there are now additional pieces where the dilaton diverges and where the gravity effectively becomes very weak. So when we think about this geometry where the constant piece is equal to 0, we now find that there's this additional region at the past horizon where the dilaton diverges. So gravity decouples there. And also in this reduction where phi 0 is not equal to 0, you find there also in this region, the dilaton diverges. So now we find that we have additional regions where gravity decouples, and we might think of using the island formula in those regions. And in particular, if I also consider the pole in this particular sort of model where phi 0 is equal to 0, then the value of the dilaton at the pole is proportional to the central charge. So when the central charge is very large, this is also a region where gravity effectively becomes weak. Okay, so what I now can do is I can use the island formula to compute the entropy in these different models. So I can consider these two different setups. So here what I'm considering, if I take the reduction where phi 0 is 0, then I consider a region that is close to the pole, and I take the central charge to be large to make sure that gravity is weak in this region. And then I can compute the entropy of the region here where radiation is collected. And then I allow for the possibility of an island to give a contribution. And I do the same thing sort of in this model where phi 0 is not equal to 0, but now I use really this region where the dilaton diverges. So then in JT gravity, then the fine-grained entropy in this model is given by the island formula, where now the entropy term is replaced by the value of the dilaton at the island. And when you extremize this formula, we indeed find that there's a non-trivial island that is located roughly where I drew it here. So it's close to x minus equal to 0, so that is this future horizon, and it's given by this particular expression for the x plus coordinate. You see that there's this time dependence that appears here. Okay, so when you evaluate the entropy using this island formula, you find that there are now two possible configurations. There, as before, there is this trivial island where the radiation entropy is just given by the standard von Neumann entropy formula. And this is an increasing thermodynamic entropy. So this is the same entropy that we saw before that was increasing for the black hole. But now there's also this non-trivial island that can give a contribution, and that leads to a decreasing horizon entropy. So then eventually the diagram that you looks very similar and to the one that you find for a black hole. But if we take the minimum of these two contributions, we find that there's this green dotted configuration that gives the entropy. So naively, it seems that also in the Sitter space, at least in this particular non-equilibrium state, the radiation follows a page curve. However, as I mentioned before, we do need to worry about backreaction because at some point it's clear that we cannot continue this process anymore because there's too much radiation that is being collected in the static patch. So we need to assess that we're still in a regime of control, basically. So when you assemble positive energy inside of the static patch, then this decreases the size of the horizon. So in this case, that is given by the size of the dilaton. So what you find is when you do this, look at this state that the dilaton size decreases as a function of time. And one sort of quick way of getting an idea of the size of the backreaction is to look at the size of the dilaton, or equivalently the gravitational entropy. What you then do is you can look at the dilaton evaluated at the horizon. And what you find is that this goes to 0 at a particular time scale, which I call T end here, which depends in the following way on phi 0 and this constant phi s that appears in the solution of the dilaton. However, the page time, sort of where we see the curve turning around, this is given by 1/3 of the value. So at first sight, you might say, it's definitely clear that if I reach this regime where SH becomes 0, because the dilaton becomes very small, there I might worry that backreaction becomes large. But because the base time is earlier than that, you might say that there seems to be an opportunity to decode some information from the radiation. However, we need to be a bit more careful than that. Because what you find is when you look at the formation, for example, of horizons in this geometry, you find that at some point there's also a trapped region that appears. So to define a trapped region, what you typically do is you look at the expansion scalar. So you define some particular space-like slice. You look at light rays that are emanating from that slice, and you look what happens with sort of their cross-sectional area if that decreases or increases when you evolve time. And then a trapped region is defined as when both outgoing null directions, this area becomes smaller. So in the case when you're doing this in JT gravity, you define these trapped regions by taking derivatives of the dilaton. And you find this particular time scale, which I call T trap here, which is scales as phi s over c times L. Then you find that there's this trapped region that appears. And as I said, so that's defined by taking null derivatives of the dilaton. So after this time scale, you find that there's this gray region that appears where a trapped region forms. And normally such regions are associated with the formation of singularities. So you might worry that at this particular time scale, there's already a singularity that forms. So it's slightly subtle in this case, because normally if you want to compute the formation of a singularity from these trapped regions, then when you use, for example, Penrose's Singularity Theorem, you always assume the null energy condition. However, in this case, we know that our quantum state violates the null energy condition, so we cannot directly use this classical result. So instead, what you need to do is to use a so-called quantum singularity theorem. So you can, for example, see these references, how to define those quantum singularity theorems. And typically, there's sort of a slight generalization of a classical singularity theorem when the null energy condition is violated. So the statement of the quantum singularity theorem goes as follows. So now we do something very similar, but instead of looking just at the behavior of the area, you now look at the behavior of the generalized entropy. So I define some point P here, and I define its generalized entropy as follows. And then a quantum trapped region is defined by now taking null derivatives of this generalized entropy. And when both derivatives are negative, then that describes a region that is quantum trapped. And then you can use a quantum singularity theorem to deduce that the spacetime must be geodesically incomplete. Hence, a singularity forms at some point in the future. So when you do this, for this particular non-equilibrium state that I described, then you indeed find that there's this quantum trapped region that now forms at a slightly different place than the sort of classically trapped region. But the time scale that when this quantum trapped region is formed is exactly the same as the time scale where this classical region becomes, or this classically trapped region forms. So what it means is that after T becomes bigger than T quantum trapped, the formation of a singularity will be unavoidable. So then when we go back to the time scales of when, for example, the island formed such that we can, for example, decode some information from the radiation, you find that the time where the island forms is exactly up to a very small, it's almost actually, it has the same scaling, I should say, as the quantum trapped region time scale. So what this means is at the moment it becomes possible for an observer to decode some information from the Hartmann radiation in the Sitter space. It's also guaranteed that that observer will not survive the experiment because there's a quantum trapped region that forms, and hence there is a singularity that forms in the future. And this also seems to in line with expectations also for high dimensional de Sitter space. So for example, in this paper, it was shown that if you want to collect enough radiation inside the static patch of a high dimensional de Sitter space, then before you can reach the spacetime where you would think that you could decode some information, you already have so much matter that you basically exceed the mass of a Nagy black hole. so you wouldn't expect to survive such an experiment. So the conclusion seems to be that in this case, also backreaction seems to prevent the static observer from surviving their curiosity to decode some information from the Hartmann radiation. So is there then no hope? It might be that there are different protocols that one can consider to describe information recovery in de Sitter space. So maybe to just mention one thing that you could try to do is to consider a similar protocol to what happens for a traversable wormhole in anti-de Sitter space. So there what you can do is you can consider a protocol where you inject some negative energy into the bulk, and that leads to a time advance for a geodesic that presses it. And that allows you to map basically information from one boundary to the other boundary. You can also try to do something similar in de Sitter space, and that is something that has been considered in these papers. So one nice thing about de Sitter space is that in contrast with anti-de Sitter space, if you have some positive energy that you send out from a pole through the horizon, then this leads to a time advance. Whereas if you would do this for anti-de Sitter with a positive energy shockwave, this would lead to a time delay. So then what you can consider, for example, is to consider the situation where I throw some information that leaves the cosmological horizon. Then I apply this positive energy shockwave. And then if there's some reflection that takes place here, then because the shockwave leads to some time advance for this geodesic, it can be net back again to the South Pole. So this seems to have some flavors of information recovery, making use of the shockwaves. And doing this experiment does not really rely on defining this dynamical quantum state. So perhaps you can use experiments like this in order to make some headway to do information recovery in de Sitter space. However, I think it's fair to say that because this is more a semi-classical experiment, its precise relationship with quantum information recovery is not completely clear. And so that would be something I think would be very interesting to understand this a bit better in future work. So that brings me to the end. So what we saw today is that understanding quantum gravity in de Sitter space poses some serious problems. But at the same time, it's a very important problem that we would like to understand better. And one way of approaching it is to make use of ideas of quantum information theory to try to sort of sharpen our understanding of quantum gravity in de Sitter space. The way we did this in particular was by considering a non-equilibrium state in de Sitter space and describe that within the context of JT gravity. And this state can be thought of as describing the situation where there's radiation that is coming into the static patch, but is not allowed to leave it. So when you compute using the island formula, the possibility of these islands that contribute to the entropy, you find that in this particular state, there are indeed islands that appear, and naively, its radiation seems to follow a Page curve. However, at the same time, when information recovery becomes possible, there's also a large backreaction in the sense that a quantum trapped region forms, which signals the existence of a singularity in the future. So even if an observer tries to decode some information from the radiation in this particular setup, then this particular observer will not live to tell you exactly what type of information they saw. Yeah, so thank you very much.
Thanks, Lars, for the very nice talk. Do we have any questions?
I guess I have a question. So this situation there with the trapped surface that forms in your geometry in this particular state, should I think of this as the sink that you put at the center of the static path as collapsing into a black hole? Is this an accurate interpretation of that trapped surface you formed there?
Yeah, I think that's an accurate description. So indeed, what happens is basically that you're collecting radiation, and what this does is this shrinks the cosmological horizon, and in this state, you're basically just continuing this until the end. So indeed, what happens at some sort of critical time where this trapped surface forms, then indeed there's so much radiation that is being collected that this indeed forms a black hole. I think that's indeed the correct interpretation.
What's the entropy of the radiation at that transition point?
So at the transition point, let's see. So it depends a bit on the model that you're looking at, I think, because this time scale where this trapped surface form scales as phi of s, so the value of the radiation is determined by basically phi 0 plus phi s. So it's slightly different in these two models. So it depends a bit sort of if you're considering sort of the model with phi 0 equal to 0 or not precisely what the value of the entropy is at the point.
The reason why I'm asking is because there's a kind of a largest size black hole you can fit inside the static patch. So there's only so much you can reduce the entropy of the static patch by putting energy in it. And I'm curious if the entropy at the transition point matches that.
Yeah, I see what you mean.
IA solution for the.
Yeah, that's not complete. I think we at some point we tried to think a bit about this. It's slightly confusing to think about it from a two-dimensional perspective, because I think what happens when you're doing the reduction from 4D to 2D, you're already considering a black hole that is very close to the Nahi limit. So I think effectively what you're doing by introducing this state is, if you think of it from a four-dimensional perspective, then what would happen is you would sort of have radiation coming in from the cosmological horizon to the black hole, but you wouldn't have any radiation that is leaving the black hole itself. So what would happen is that this black hole would increase. And I think if you would continue this process, then the black hole horizon would basically exceed the cosmological horizon. So from a four-dimensional perspective, it leads to this pathological situation where you would probably see the singularity of the black hole. So I guess that's maybe sort of a different way maybe of seeing why the singularity should form.
Could I ask for a little bit of elaboration on what is meant by the formation of a singularity here? So by that I mean, so this model, the matter that you're introducing, it doesn't couple to the dilaton, right?
So what did you say, the matter that's not coupled to the dilaton?
Yeah. So first question, the matter is not coupling to the dilaton, is that correct?
I think so. The dilaton, it depends on the central charge. So I would say that there's a coupling there.
Okay. Because what I was wondering is, like, if it doesn't couple to the dilaton, then the dilaton equation of motion is still just going to give that R is equal to +2 everywhere.
Yeah, so that's a good point. So that's indeed sort of a peculiarity, I guess, of 2D gravity that I mean the metric is fixed because indeed. Because you're doing 2D gravity, so all the dynamics is in the dilaton. So it's a bit, so when you would say, I would compute, for example, if there's a singularity formation based on the metric, that would give you the result that nothing really happens. So I think the appropriate thing to do in this case is to really look at a dilaton. So in that case, the way you sort of signal the fact if there's a singularity or not is basically given by the size of the dilaton. So what we did here were a bit more, I guess, sophisticated to sort of use this quantum singularity theorem, where you use the generalized entropy to say if there's sort of a region that becomes geodesically incomplete. Where in this case, I guess it's a bit strange to talk about geodesics because you're considering the dilaton and not exactly the metric itself.
So in this case, when you say that a singularity is developing, what I should be thinking is that the dilaton is doing something weird in this case.
Yeah, maybe exactly. So that's maybe the easiest way of thinking about it. Indeed, is when we, for example, take this figure and we look at the dilaton, and you find that the dilaton becomes smaller and smaller. So if you would go sort of to this point here, far in the future, you find that the dilaton goes to -infinity.
I see. And does the quantum singularity theorem then, does it have anything to do with the size of the dilaton? Or should I think of that as being like, okay, well, we see the conditions for the quantum singularity theorem being fulfilled, thus else I should take that as intuition that maybe something similar would happen in higher dimensions where I actually can form curvature singularities.
Yeah, so I think it's indeed the quantum singularity theorem. Normally, there's this area piece that you compute. So in this case, it's now given by the value of the dilaton. The computer generalized entropy. So that's indeed how it arises.
Is there a Euclidean path integral construction of your non-equilibrium state?
Not that I'm aware of. It seems tricky because it's time dependent. So that's something that you need to worry about. And then there's the singularity and the past horizon. So I think maybe the singular.
I think this time dependence is crucial because he's violating the non-energy condition, right? So he wouldn't write down a state. It's a dynamical setup in which you can violate this. You can write down a state that violates it. It's a statement about the particular history that you're constructing with this sink at the center.
No, there's a non-equilibrium state that's under consideration, right?
Yeah.
I agree. The property of the violation is a property of the history.
Yeah. So
I think there's some time of
the initial state.
Yeah.
Okay.
Yeah. The reason I asked just because you could try to prove that the island formula applies to your setup, right?
Yeah, so that's tricky. So I think maybe sort of the simpler question that you could try to ask is to first do the sort of the Euclidean prescription or description of the standard Unruh state for a black hole, because that basically shares many of the same features. Because there it's also the case that you sort of shut off one direction of the radiation. So I guess that might help you to give some way of how you should think about it also in the sitar context.
Thanks.
Do you have any other questions for Lars? If not, let's thank him one more time.
Yeah, thanks for having me.